Today's topic is going to focus very specifically on one kind of reaction, and this is a table that's in your data booklet. We're going to focus. Guys, give me your focus, please. Okay. We're going to focus very specifically on formation reactions. Okay. The way that they're going to structure a lot of questions is they'll ask specifically the formation ones because there's that whole table in your data book. So if you guys can, just flip to that table because we're going to reference it a lot over the next hour or so. What is a formation reaction?
Like form two things to create one more thing?
Sure. When you guys learned this in grade 10, probably, it was like A plus B becomes AB. Does that make sense? Right. So here's a good example of a formation reaction. Hydrogen gas adds to oxygen gas to form liquid water. That makes sense? So that's a formation reaction. Okay. What we're going to do here is we're going to assign some numbers now to each individual element in the reaction. Okay. And this may sound kind of dumb at first, so just bear with me, okay? We're going to assign hydrogen 0, thereby meaning that you cannot try to form hydrogen gas. Because hydrogen gas is already as low as it can get. It's already an element. Does that make sense? So that's what this statement here is. The enthalpy for elements is going to be defined as 0. This hydrogen right here, you can't form hydrogen. It already is as low as it can get on the periodic table. It already is an element.
You can't break down hydrogen.
Does that make sense? Oxygen is also an element. So you can't break oxygen down anything lower than its elemental form. But water is a compound. So water is going to be defined as the 285.8. This number right here is hopefully the number that's in your data booklet for water. If you want to just look it up here. By the way, state of matter does matter. Matter does matter.
Why?
So there's like a liquid and gas version. Okay. So the liquid version is hopefully 285.8 kilojoules. I believe your data booklet is going to say per mole.
Yes.
But why does this one not say per mole?
Because it's just one.
Because there's only one sitting right there. Okay. So the way this thing works is this number right here is going to be assigned to just the water. And these guys right here, we're going to assign the numbers of 0. Does that work so far? Okay. Let me try another example here then. Let's say I asked you to form delta H for the formation reaction per mole of MgO. So you can find this number in your data booklet if you can look up where magnesium oxide is. Negative 601. Thank you. Kilojoules per mole. Okay. When we're writing out this equation then, magnesium oxide is going to be formed from what?
Magnesium solid and oxygen gas.
Magnesium solid. I'm going to do a half an oxygen gas. The reason why I'm going to choose to do a half an oxygen gas is now the ratio is 1 to 1/2 to 1. Okay. And what this means then is that this number will be assigned a value of 0 because you really can't form magnesium. That makes sense? This number will be assigned a value of 0 because you really can't form oxygen. And then this number right here, if this was 601.6 kilojoules per mole, then since I have 1 mole written right here, this guy will be 601.6. What if I didn't write it in this format where like I have the 1/2? What if you say we don't work with 1/2? So what if you wrote it as like 2 magnesiums plus 1 oxygen forms 2 magnesium oxides? Yeah, then this number would be doubled, so it'd be like what, negative 1203.2? And these guys will still be assigned zeros. Does that make sense?
That makes lots of sense.
Okay, good. Okay, some kids struggle with that. Okay, pause on that thought for a while here. I want to show you guys a diploma question. We're not going to be able to solve it yet, but we will in a second. Okay. Here is a question that was on a diploma once. It basically said, here's an equation. Tell me what the enthalpy per mole is. And it gave you no numbers whatsoever to work with. Very frustrating. It was like, if you had Q equals MC delta T, maybe you could do something with it. If you had some other numbers, you could do something with it, but it gave you nothing to go off of.
Do you make one side equal something, or
Do you have to like make ethanol?
You have to make up numbers in your like equation using some of these values here. Okay. So using a similar principle to what I just did there, right here you are forming carbon dioxide.
Can you look on here and find it?
So I need for you guys to look in there and figure out how much energy carbon dioxide takes to form.
Negative 393.
Okay, so it's negative 393.5, but that's kilojoules per mole.
3 times that by 8.
Good. So you have to times it by 8.
You're wrong.
I
Okay.
can't do that now.
Well, hold off on that. Let's not find that number just yet. Okay. Here's water as a water vapor. Now, if you wanted to form water, what would it take?
Maybe 241.8.
241.8. But again, that's kilojoules per mole, so you have to times by 10. Do those two make sense to start? Okay, now the next twist. These guys right here may also have numbers in your data booklet. But are these things here being formed?
No, they're being broken down.
Okay, so kind of like Hess's law, it's going to be the opposite here. These guys right here, if we can find their numbers in the data book, but they're not being formed, they're being like
So
decomposed.
they're just like opposite the charge.
Opposite the number, yes. So find me butane in here. What's butane's number?
Negative 1.
Negative 1,
25.
25.7. Okay, so that's what the number would have been if you were forming butane. But you're not forming butane, you're decomposing it. So we're going to make it positive and times by 2.
It's just as simple as that?
It is, yes.
Okay.
One more thought here. Find me oxygen in the book.
No.
Good.
0.
Why is it 0?
Because it's oxygen.
Because it's an
Oh, yeah.
element, which I just did that last slide. Things that are elements, you really can't form oxygen because it already is an element.
And then we just add them up and then divide.
Add them up, and actually that's actually it. Although since it wanted for the combustion of ethanol, we're then going to re-divide by 2 because there's a 2 right there. So, but before we do that though, let's actually just like put all this stuff together. So times this guy by 2, times this guy by 8 as a negative number, times this guy by 10 as a negative number, and just find what all of that is as a number.
Like add them up together?
Yeah, add them all up together.
Then we have to divide by. Wait, what are we dividing by?
Well, let's do the divide by in a second. So just hold off on the dividing number just for 1 minute.
Okay.
So when I put all of this together, I got an answer of negative 5314.6.
Yeah. It makes sense that it doesn't know.
Did you guys get that value?
Yeah.
So it's C.
Well, no, it's not C. C is meant to throw you off. This is how many kilojoules you get total. But it wanted kilojoules per mole of ethanol. That's where that, again, we got to think about, well, which specific guy are we talking about? Since we're talking about this.
Yep.
Is that ethanol right there?
That's butane.
That's butane.
Oh, what?
What did I screw up here? Let's pretend that this said of butane. That must be some sort of mistake here.
That's weird.
That is weird. Anyways, let's say it's of butane then. I don't know why it said that. Then we would then divide this thing by 2, which means the answer should have been that guy.
Yeah. Do you think that's like supposed to be like that, or do you think it's?
I wonder whether I accidentally took the top half of one question and the bottom half of another question.
Oh.
I'm wondering here.
But it.
Yeah, but
Because this talks about disposable lighters and butane gas. And this talks about burning ethanol in automobiles. So I feel like I screwed something else up, or there's a typo somewhere.
Well, maybe just
But how
the
do-
question itself, though, not the answer.
Yeah, but we
Yeah.
got an answer, so it's like.
Yeah,
I feel like this was a typo. This is supposed to be butane.
Yeah.
Okay. Yeah, that's weird.
I'm sure it must be a
That
typo.
would suck if that was a diploma
Yeah.
question and you just. Yeah.
Okay. Does that concept make sense though?
Yes.
Okay. What you're doing is essentially Hess's law. Hess's law says that if you need to like add and subtract reactions, that's a valid way of like putting together a different reaction. The rules for Hess's law are if you need to, times by 2 or 3 or 4 or 5. And that's what we did right here. Your data booklet gives you the enthalpy per 1 mole of carbon dioxide. So that's why you had to times by 8. It gives you the enthalpy for 1 mole of hydrogen or of water. So you had to times by 10. Your data booklet gives you butane as though it's being formed, but you don't want to form this thing. So what you're really doing is taking the reaction and flipping it the other way around. Does that make sense? So the reason I want to show you this question here in particular is often kids will look at this question and just freak out, going, how do I solve this? I have no numbers to work with. The truth is, you have all sorts of numbers hidden in your data booklet that can be used to help you solve questions. Does that make sense? Just a couple of notes on this thing. If you ever see the word thermal stability, you can actually figure out thermal stability based on these guys here. Let's say you have a compound, and that compound is going to like break down. Okay, is that formation or decomposition? That's decomposition. Okay. Now your data booklet lists formation reactions, but those guys are opposites of each other. Does that make sense?
That's why we just switched them.
That's why we're just going to switch little sides. Okay. The way this works here is that most compounds are formed exothermically from their elements, so the numbers are negative. Okay. Meaning that when you form something, it releases energy. That makes sense? If you look at all these numbers in your data booklet, when you form them, they release energy. Therefore, if you're going to try to decompose them, it's going to require energy. I'll say that one more time. Most of the numbers in your data booklet for formation are negative, meaning that when you form something, you release energy. Therefore, if you're decomposing something, it requires energy. Does that logic make sense?
Yeah.
Okay. If you're going to be very stable, it means that it takes a lot of energy to decompose you. So if you want to figure out which of these things on your data booklet are the most stable, look for the largest negative number. Those things are very, very stable compounds. So like find me an example of a number on your data booklet that's very, very negative.
Magnesium sulfate.
Sure. What's magnesium sulfate's value there?
1284.9.
Okay, so magnesium sulfate is negative 1200. What that means is that if you wanted to form magnesium sulfate, it would release 1200 kilojoules of energy.
How is some positive?
Some are the opposite for, I don't actually have a great reason for it, to be honest right now. But do you agree that most are negative though?
Yeah.
Okay, so if you have a large negative number for forming it, it means when you form, it gives off energy. So if you form something that gives off energy, then if you decompose it, it should require energy. The more energy something requires to decompose, the more stable it is. Long story short, big negative numbers equals stable.
In formation.
In formation reactions, yeah. So in your data table, the larger the negative number, the more stable it is.
So water is not that stable.
Well, actually, it's fairly stable. Like it's a 200, right?
Yeah, there's some that are like 60 or.
Does water just randomly decompose into hydrogen and oxygen?
No.
You can actually make it though. If you do electrolysis of water, you ever seen that before? You can make it turn into oxygen and hydrogen gas. But it's going to require some energy for it to do that. Okay. Okay, here's a more typical example. I might give you an equation and say, find me the delta H for the reaction. So right off the bat, you might say, I don't have enough information. And I might point out to you, you have a data table. So, do you have calcium oxide in your data table?
We do.
Perfect. What's the value?
Negative 634.
Okay, well it was negative 634.9, but your data table is all about forming things. This calcium oxide is actually going to want to decompose and break apart. So we're going to have to flip that value, and I'm going to times by 1, because there's 1.
Wait a minute, isn't this forming? Yeah, but
Sorry, did I do it wrong? So this thing right here, we need to have it decompose.
Because it's not just calcium.
Because these things are decomposing, and these things are being formed. Like reactants are being broken apart,
Okay.
and products are being formed.
So if you're decomposing like say a positive number, would you make it?
It would become negative. Liquid water.
285.8.
Okay, well it's a negative 285.8, right?
Yeah.
But that is if you're forming water. But as a reactant, reactants actually have to break apart, so we'll have to flip this guy to positive. And again, times by 1, which is pointless. Calcium hydroxide. 985.2. And was that negative?
Yeah.
Okay. And this one we're going to leave as negative because the calcium hydroxide is actually being formed.
Oh.
Basic rules then, whatever the coefficients are, times by the coefficients. Products, don't do anything to. Just leave them alone. Reactants, flip.
And then you just add it all together.
And put it all together.
Really?
That's it. That's why I only have like 3 slides on this, because once you've done it 2 or 3 times, it's the same thing. So 634.9 times 1 plus 285.8 times 1 minus 985.2 times 1. I got negative 64.5
And that's kilojoules?
kilojoules. Now, if I wanted it per mole, we could do it per mole.
But you'd have to know which one.
Sure. I mean, either way, it's dividing by 1. So,
Wait, one.
well, because
They're
like,
all of
because
one.
they're all a 1,
Oh, yeah.
right? So either way, if it's per mole, it's divided by 1. But does that make sense? Okay, so let's try a different question here. Let's not give you an equation written out. Let's write it ourselves. Methane is burnt in power plants. We want to figure out what the combustion of methane should be. So, anyone know what methane's formula is? Kiddo?
Yeah.
Do you have a dictionary for that? CH4. If you combust CH4, you're adding it to oxygen. You're making CO2 and water. And when you combust water, the state of matter is gonna really matter.
Is it down or is it gas or is it liquid?
It'll be gas. It said water vapor as a product. The way I remember that though is when things blow up, they usually don't blow up and make liquids. They usually blow up as gases. So. Okay. Can I use this equation as is though?
No.
Not until it's balanced. So make sure you balance first. Alright, that problem solved. Okay, so let's start with methane over here. Does methane have a value in your data booklet? Okay, well I'm going to make it positive 74.6 then. Because it is going to need to be decomposed rather than formed.
Go to 0.
Good, oxygen is 0. Write that down somewhere. I always get asked this question. Someone will ask me like, I can't find oxygen. And I'll point out oxygen's not in there because it's an element. So write some sort of note. Elements are defined as 0. Carbon dioxide is negative 393.5. What's water gas?
241.8.
241.8. And times that by 2.
Oh,
I got negative 800.7. Anybody else get that?
oh, no.
Nope.
43.6.
802.8.
Yeah,
60.7.
I got you.
You forgot to times it by 2. I think.
Yeah. Oh, we're
I
adding
did
it all
that
up
too.
now. I'm sorry. I'm totally wrong. I
I
got
did that
7.
too.
No.
Okay, 802.5?
Yeah.
Okay, there we go. I messed up last time. Negative 802.5. Now that's in kilojoules. One last thing here. It wanted to know the molar combustion of methane.
It's the same.
So then this equation for methane is written as a 1. So then you can just write it per 1 mole. But if this thing was a 2 or 3 or 4, you'd have to divide by
Who said
2 or 3 or 4.
So I get confused when you divide and you multiply.
If you're given a molar enthalpy, like if you're given it as something per mole, then you're going to times by the 2 or 3 or 4 there. But if you're given this just kilojoules and you want to make it per mole, then you'll have to divide by whatever that number is there. So it depends on whether you...
Because that's just kilojoules of the combustion. Okay, I got it.
Works.
Makes sense, yeah.
Okay, one last thought here. I think you guys have this slide as well. This is the last one, right? Okay. I could then ask you to tell me how this fits onto like a graph. Okay. And so I think I showed you guys this before. They might give you a graph where they give you like some numbers here sitting on the side. And then like the difference between those numbers, if you subtract, would be the delta H for the reaction. Does that make sense? So if you were to subtract like the difference between 877.1 and 74.6, you'd get 802.5. Does that make sense? Like subtracting these numbers from each other. And then I'll make it negative because it's going down.
Yes.
Okay. So what this means then is there are three main ways that you can find enthalpy stuff for reactions. The first way is you do an experiment using Q equals MC delta T, which is kind of what we did in our previous two labs. A second way of doing this is with Hess's law, which is what we did yesterday, where the reaction you want to do, for whatever reason, you can't do that reaction. So you do this reaction, you do this reaction, you manipulate it so stuff cancels, and that's another way to find a reaction that you're looking for. This is now a third way of finding a change in enthalpy for a reaction. And this way should always work if all of the things that you're looking for are in your data booklet. Does that make sense?
Will there be questions where they're not?
Yes. That was gonna be my next point.
Guaranteed there will be?
Yes, they like to throw on questions where, so that you can't use your data booklet for everything, they throw on things that aren't in your data booklet, so it forces you to either do the Q equals MC delta T method or the Hess's law method. Does that make sense?
Which is
Because otherwise, you'd just do this for everything.
Yes.
Does that make sense? Because this way is actually pretty easy, which is why I show you it last. All right. Does that make sense? Okay. We've got half an hour left. A couple things to work on then. Tomorrow we're going to do another lab. Here's some textbook pages. If you have a SNAP workbook or if you want to use one of those, there's some good questions in there. I also have another worksheet that I printed off. Maybe it's on the printer that you guys can do.